It was nice. Yeah. So in this video, let's make a derivation the one-dimensional Euler Lagrange equation, and in the future that we will derive like multi-dimensional version of this results. Okay. So just for fun, hope you guys subscribe to my channel. Okay. So derivation is not so rigorous, but it's fine that hopefully it's good for you. It's enough for you. Okay. Okay. So yeah, let me just change it. Okay. So the idea is the following, right? So let's say for one-dimensional version that you're interested in a variable j. Its number basically there's a to b. So the one-dimensional, and then you have x, fx, and the differentiation respect x, dx. Okay, and then you are subject to like, so you have a function f and the functional L. And you are require that f is like fixed at 2 points, for example, from a to b, and you're a and b. So you force that f must be any function which is differentiable from this. So we require fa equals to a and fb equals to b. In the middle, there can be any differentiable function. Okay. So one answer is that the idea, and we want to find the maximum or minimum of j. So it's the same as like when you start in calculus, right? So that's working some simple case. But if you're working on some calculus, for example, let's say you do this, how do you find a minimum of it, right? So one idea is that you assume minimum is some particular x0 or x naught. So let's say x naught is like maximum or minimum, and then you ask what is the x naught plus an epsilon, right? So this is like the perturbation, little bit perturbation, and you want to say that these points, right, respect to this perturbation 0, will give you the maximum. Okay, so you can do this. Okay, and the things is linear, right? So you can write as this. Okay, and you can see that then you want that the perturbation to be 0, right? So which you solve x naught is 1. So basically, this is the same as what to the differentiation. Okay, so in this case, that we can assume that our f of x is some particular answer, right? So but some particular answer plus epsilon times some function. Okay, it's arbitrary function. So it's natural to just write. Let's say, right, let me just change the notation a little bit. Let's change this to be g. And then let's write our g to be f of x plus epsilon eta of x. And we want to like approach, we want to make compute j differential respect to eta, respect to epsilon, right? So we want to do this and set it to be 0. So this condition will let me have an equation to solve f. It's the same as that when you use epsilon to be 0, then you can have some equation to solve x naught. So the idea is that similar to this. Well, the proof is just this. Okay, so you can write your j epsilon to be like a to b, let's say L and x, g epsilon derivative. So remember this derivative on x. Okay, so now I can write the following. So the thing is there's only one variable, so I can just write a simple differentiation. And then in this case, you need to exchange the integration with the integral. So it's like you need some uniform convergence. Basically, you need some advanced calculus to help you, but let's forget about the detail. Let's say you do this. So you will have like partial x is not important, right? So you get partial g, and the g epsilon. So remember, g epsilon is f plus epsilon eta. So when you do the differentiation respect to g epsilon, you get this, and so also you get this and this. Okay, so in this case, that you should get the a and the b, and this dl divided by dl partial dl dg is fixed, and then this guy you get eta, and then this guy you get what? You can do a differential with respect to x. Remember it's x. Okay, so you get eta prime. Okay, and then do a dx. Okay, now you can use the partial integration or integration by part. Okay, so let's say plus. Right, so if you want to use integration by part, that you can use this minus minus what? Minus the other direction, right? So sorry, I'm stupid. Yeah, I haven't been a while to do this stupid things. So since it's x, right? So we need to like do the integration on this. So let's write down. So we have d eta d eta prime dx and the dx. Okay, so let's do this. So we have this. Let's write this. Let's write this to be this dx. So this is no prime. So we get partial L partial G prime eta minus minus the ddx partial L partial G prime eta, right? Dx. Okay, and then this term that I can, since it's total derivative, right? So there's a dx here, so I can pull out eta, and I probably plug a to b. Okay, and then this is 0, right? Because by my constraint that I need to fix that g the epsilon and f epsilon to be then f to be at a boundary. So boundary is fixed point, so this term will be 0. So that means this integral can be replaced by minus d dx partial L partial G prime eta dx. Okay, so you combine both, then you get the following, right? So if you do the dj eta d epsilon equals 0, then you can derive ab partial L partial G prime minus ddx, right? dx partial L partial G prime with eta of x dx, and this eta of x is arbitrary, right? So you can use maybe you can use like any theorem. One theorem is that there's a theorem if f is continuous. It's some exercise at the analytic that's analytic course. So if you have f is continuous on AB, and you have AB f of x and 0 for every n greater or equal to 0, then you can prove that f is 0. So using the Weierstrass approximation theorem. So at any compact interval, the continuous function can be approximated by arbitrary polynomial. Okay, so you can use the Weierstrass. We can use the Weierstrass approximation theorem. And obviously that this eta can be chosen to be all the polynomial. So this directly shows this. Okay, so this is a one-dimensional proof of this Euler Lagrange. And yeah, that's it. So yeah, so it's like when you write L, then you can write down this, and you will have some ODE, right? So it should be ODE, or sometimes the higher dimension will be PDE, that you can solve for a particular function G, which make this J to be minimum or maximum. Okay, so see you guys next videos. Hope you guys subscribe to my channel.